Find the eigenpairs of the BVP. Y double prime plus lambda y0, y at 0, 0, y at pi plus y prime at pi equals 0. So we need to consider three cases. Here lambda positive, 0, or negative. So let's consider lambda equals 0. That means this ODE becomes y double prime 0. Solve, integrate one time, we get y prime, let's say variable x, that will be just a. Integrate one more time, so y is ax plus b. Now use first initial condition, y at 0 equals 0. That would imply y is 0 when x is 0. So this is 0 plus b, so b is 0. Now use second initial condition, I meant boundary condition, then a is also 0. So lambda equals 0 is not an eigenvalue, so we don't get any non-trivial solution. In the same way, you can try for lambda negative. We can say lambda negative mu square, where mu being positive, then or again you will get no solution or trivial solution case. Okay, now the third case will be then lambda positive. To avoid writing square root, we can take lambda mu square, where mu is positive. In this case, the ODE is y double prime plus mu square y equals 0. To solve this, we find characteristic equation, which happens to be r square plus mu square 0. Subtract mu square from both sides, take square root, so r is plus minus mu I. Okay, so based on this we get solution y is c1 cosine mu x plus c2 sine mu x. Looking at the second boundary condition, we got y prime, so we need to find its derivative. Then y prime, cosine means negative sine, so negative mu c1 sine mu x plus mu c2 cosine mu x. Now using the first boundary condition, y at 0 equals 0, that means we use here using y at 0 equals 0. So this y is 0 when x is 0, so c1 cosine 0, cosine 0 is 1, so the c1 plus c2 times sine 0. Sine 0 is 0, so this is just 0. This implies c1 0. Now we can go back and update our solution, because c1 is 0, so we don't have this anymore. In the same way, y prime, c1 is 0, so we don't have this anymore. Now we need to determine c2. For that we take second boundary condition. So using the second boundary condition, y at pi plus y prime at pi equals 0, this implies, so we combine two different terms and that's 0. So let me write 0 in the front. 0 equals y at pi. Y means we need to use here, so y at pi means c2 sine mu pi, c2 sine mu pi, sine mu pi. That's the y at pi, plus y prime at pi, so that's here. Okay, so x is pi, so this is mu c2 cosine mu pi. Okay, that equals 0. I wrote 0 in the left side. So from this, okay, look at here, C2, we can factor C2 out. That leaves sine mu pi plus mu cosine mu pi equals 0. If we take C2 0, then we get trivial solution, but this expression can be 0 at certain places. Okay, so we take C2 not 0, C2 not 0. Okay, that implies this 0. So sine mu pi plus mu cosine mu pi equals 0. This is called determinantal equation, because from this we can determine mu. For let's move sine to the other side, negative sign, and divide by cosine. So this implies mu equals negative sine divided by cosine, means tangent mu x. Now to solve this equation, we graph two functions. So the graph is here, in fact. So we take y equals x. So this one first, mu, means we can take is just simply x. So this one is y1 first curve equals x, and second curve is negative tangent. Okay, this mu is x, so I made a mistake here. It's a mu pi. Okay, not mu x. This is mu pi. So y1 equals x. Anyway, this is x. So this one is negative tangent pi x, because mu is the variable. Okay, that's what we are trying to determine here. So these graphs, okay, this is identity line. I did not show the origin here, so somewhere here. Okay, this is identity line, y1 equals x. Second curve, these lines. By the way, the pi is already there, so pi over 2, tangent pi over 2 is undefined, so we get vertical asymptote at pi over 2. So at 1/2, look at this graph. At 1/2, this is 0.5, that's 1/2. This is 3/2, this is 5/2, 7/2, 9/2, and 11/2. These are the places where we get vertical asymptotes, because pi is already there. If we had just tangent pi, then we would get pi over 2, 3 pi over 2, 7 pi, 5 pi over 2, etc. And now if we look at closely this graph and the second graph, these are y equals, in fact these are, I graph y2 equals negative tangent, this mu is x, pi x. So I graph this and we get these curves, and here is the first point of intersection. So lambda 1 will be here, mu will be here. Okay, that is the point, and second is here, that's the first point of intersection, mu 1, that means in fact this distance, and this is mu 2, here is mu 3, mu 4, and mu 5. If we look at closely, these points of intersections are coming closer to these lines. Okay, these are vertical asymptotes. Okay, so using calculator you can find this point of intersection mu, and in fact the eigen value lambda is mu square. We need to square. Okay, so you just find using your calculator and find this, but for large n we can see mu n will be approximately equal to like 3 is 5/2, close to 5/2, 4 is close to 7/2, so that is 2n minus 1 over 2. Okay, mu 3 means this is 5/2. Okay, 3 is close to 5/2. mu4 would be 7/2. Okay, we don't have pi here because the graph tangent pi. Okay, this is for large, okay, large n. Okay, so, and for these two you find that. So eigenvalues, so we can find now eigenvalues, lambda n, in fact we found all of them, that's mu squared, so this is square, 2n minus 1 squared over 4 for large n. Okay, n large. And the Eigen Functions, that's the solution, by the way. Eigen Functions, let's go up here. So the solution is y, these are given here, c2 sine mu x, and we can, these are arbitrary constants, so we can get rid of them, sine mu x. Okay, so these are, we can think y n sine mu. Mu we found for large n, 2n minus 1 over 2 x. Okay, these are the solution for n large enough, and these are the eigenpairs.